Hello everybody. Today we move on to the fourth lecture in our series of search methods in artificial intelligence and talk about game tree search. Just to revise, the heuristic search paradigm is modeled in the following manner. Every problem which is a general purpose problem solving paradigm, here there is a state configuration or a state or a configuration which consists of a set of variables which define a state or a configuration, and domains for every variable, and the constraints among them define valid states. Then the problem space itself is defined by a set of state transformation rules or moves, which is a rule which, given a particular state as input, which is the present state, produces the set of next states. It also indicates whether these moves are OR moves or AND moves. An OR move is when there is only one player and this player has a choice to make. However, when there are multiple players or you are playing against the environment or there is a probabilistic issue involved, then some nodes can be choice moves or OR moves, whereas some other nodes may not be choice moves, where you have to consider all of them, and therefore they are known as AND nodes. And we have discussed them in great details in the previous lectures. The state configuration and the state transformation rules define an implicit state space graph. And this implicit state space graph is to be searched for a solution given a start or an initial state and a goal state definition. And depending on whether it's a pure OR graph where the solution is a path, if it is an AND OR graph, then a solution is a subgraph. The other important thing of search is the use of problem-specific or domain-specific information called heuristics. And these give us, as we have seen in the previous algorithm, estimates of the cost of a particular state to the goal. And heuristic search algorithms utilize this heuristic information to quickly search the state space without opening up the complete implicit state space. And we have already discussed algorithm A star, we have discussed depth first branch and bound, we have discussed IDA star. Today we move to a special case of such state space graphs which are called game trees. And we shall discuss the search algorithms and the issues involved in searching game trees. Let us just quickly look at games. Here are three games that I have put in. The first game is the game of chess. This is a two-player game. It is a perfect information game, which means that both the players have the complete information of the state space. And in this, every player can make a sequence of moves. And as they go on making a move, the end of the game can be either a win for a particular person. If it is a win for a black, then it is the loss for the white, and vice versa. Or it can be a draw for both. The second game is the famous tic-tac-toe, which is again a two-player perfect information game where two players play by putting noughts and crosses. And here also we have these three possibilities. Either one player wins and one player loses, or both end in a draw. This is the famous Go game, which is again another perfect information game for two players. So we have one category of games which are board games, where the state configuration is defined, and then there are the state space rules or the state transformation rules, which define a large implicit space. Both chess and Go are very complex games with innumerably large size of the state space. Obviously, the tic-tac-toe is a small and a trivial game in that sense. A second category of games are what are called multiplayer games. This is the famous Chinese checkers. Here, as we can see in this particular case, there are 6 players. This is also a perfect information game. And finally, one of the players wins. So here is a game which is got a set of players, 6 players, and each of these players sequentially play the game. That means after the green player plays, then the yellow player plays, then the purple player plays, then the blue player, then the red player, and then the pink player, and then again the green player starts playing. This is the game of bridge in cards. This again is a 4-player game, but most interestingly, there are 2 teams. That means there is competition between 2 teams. So while there are 4 players, 2 players each collaborate with each other. Secondly, this is not a perfect information game. This is an incomplete game. Incomplete information game, because here the cards are known only to their individual players and they can only guess what the cards are there with the opponent. So now we have multiplayer games. The games here in the previous cases, every move was deterministic. But here are 2 games. The famous game of Ludo, where the outcome is based on chance. A die is rolled, and out of 1 to 6 of these faces, something will happen, and based on this, the number of moves can be made. Here again, we have got 4 players. But the interesting thing is that while every player plays, every player's move is determined by some probability. You cannot exactly decide your move. You are constrained on your move in terms of the roll of that die. Here is the famous control problem that we talked about, control plant. In this control plant, as we have discussed the other day, there are a set of variables which define the state space. These variables are of 2 categories: observable and controllable. Now, in this control plant, some of the variables are observable and some of the variables are not observable. Similarly, some of the variables are controllable and some of the variables are not controllable, which means that the person who is trying to control this plant has got imperfect information, imperfect or incomplete information. Secondly, once a person takes a particular move by which that they are going to decide on one of the controllable variables and set its value, the values of the other variables which are not controllable will depend on the situation of the plant, and therefore this is like a game with an environment. The environment is not necessarily your opponent, but the environment can react in many ways, and therefore there is a probabilistic chance of the environment reacting in a particular way. We have discussed another problem earlier in autonomous driving. For example, in driving, if you suppose you press the brake, so let us take another example of driving. Now, if you press the brake, there is 99.5% chance that the car will stop. But there is a 0.5% chance probably that the brake may fail. Therefore, given the action of one of the players, the environment may take another action. So there is a probability involved in these games. So these games pan out to become probabilistic games. The Ludo has got a probabilistic move, then a deterministic move, whereas a driving or a control plant has got a deterministic move, and then there is a probabilistic outcome for it. Today, we see robos playing games. And when robos play games, then it's a very completely different situation altogether. So here, you have got multiple players. Here, you have got things happening simultaneously. Here, you have got both deterministic and probabilistic outcomes. You have got multiple players, but you have got teams, which means that there is both collaboration and competition. And finally, this is the full spatio-temporal space, which means that the whole state space is extremely large even for a single state. In order to address game playing, we take up a very classical problem, and this classical problem is known as the prisoner's dilemma. The problem statement is as follows. Two members of a criminal gang are arrested and imprisoned. Each prisoner is in a different confinement and they have no chance of communicating with each other. So which means that two people have been caught, they have been put into two different cells, they cannot talk to each other. Now the police or the prosecutors who have caught them lack sufficient evidence to convict on the main charge. So there is a main charge and there are some smaller charges. But they have enough evidence to convict both of them on smaller charges. However, if one of them reveals something against the other, then the conviction of a larger charge on the other can happen. Therefore, there is a trade-off and a decision has to be taken by both these players or both these prisoners, which is enunciated in this table. The table says that there are four options. Both of them cooperate with the police. That means they cooperate with each other. That means they do not reveal anything else. Then only on the smaller charge can both be charged and both can get a maximum of 1 year each. On the other hand, if prisoner A remains silent and prisoner B betrays A, then prisoner A gets 3 years and prisoner B goes free because he has become a state witness. So if both remain silent, a smaller charge is given to both. If A remains silent and B is betrayed, B betrays A, then A gets 3 years and B goes free. On the other hand, if A betrays B, then A goes free and B gets 3 years. And if both betray each other, both get 2 years. This is how the whole system is panned out. Now we see and try to determine how they will play. Looking at it upfront, it appears that this is the best option for both of them. But will they play this option? Let us see and analyze it further. We will notice, let us look at it from prisoner A's point of view. So prisoner A knows that if prisoner A remains silent, then prisoner B can remain silent or prisoner B can betray A. In the worst case, prisoner B will betray A and A will get 3 years. On the other hand, if A thinks that A will betray B, then if B remains silent, A goes free, and in the worst case, if B betrays A gets 2 years. So if we look at it from A's point of view, A has got 2 worst case options. The first worst case option is 3 years, where A remains silent. The second worst case option is 2 years, where A betrays B. So looking at A's own worst case, A will clearly betray B. So they will not reach this solution because of the fear that the other side may play out the worst case. So we model this by using the following paradigm. We create a state space graph with 2 kinds of nodes. One, this kind of node for A, and this kind of node for B. And we look at this from the table, we look at all the options. And we see that if this is cooperates, if A cooperates, then B can cooperate or defect. If A defects, then B can cooperate or defect. And these are all the results for A. Since these are all the results for A, then B will obviously put A into the worst case and produce 3, this direction. Here also B will produce the worst case. This is how A will analyze. And therefore, this and this will give you option of 2 years and 3 years, and from here A will choose the best case. So for A, this is an OR node and this is an AND node from the point of view of A, because they have to look at both the options here and find out the worst case. On the other hand, for A, this is an OR node. And from here we can see that A will choose this option by choosing the best of the OR nodes. Whereas in both these cases of B will choose their best option, which is the worst option of A. This is how the game tree becomes an AND OR tree and is drawn up. We could draw the tree also from B's point of view, and I leave it as an exercise to see that if you draw it from B's point of view, you will get and reach the same solution. So games pan out, game trees pan out in all of these. This is the tic-tac-toe, where given this start state, which is the turn of a node like this, who will mark crosses, and this is the second player. Again, this is the turn of the first player. This is the turn of the second player. And we can see that we have defined if the first player wins, we put a +1. If the first player loses, so this is win. If the first player loses, we put, and if it is a draw, we put 0. So this node is where the first player wins. So this is +1. This is another place which is a draw, which is 0. This is a place which is a draw, which is 0. This is another place where the first player wins, which is a 1. Similarly, here which we have seen is where the second player wins, which is a -1. Here again the second player wins, which is a -1. Here these are all derived from the lower place. So these are the nodes where decisions are taken, and in order for this player to play, this player who wants to win will try to maximize, and this player will try to minimize. So this will be an AND node for this player, whereas this will be an OR node for this player. This is how AND or game trees, which are also known as min-max trees, are developed. The game of chess is a much more complicated version, where again we have just marked few options here. This is player 1 and this is player 2, again player 1 and again player 2 rotates, alternate to produce, and some of these are the leaf nodes where results are obtained. So a game tree has got 3 types of nodes. Terminal nodes, which are decisions, win, draw, loss, or whatever gain you get, like in the prisoner's dilemma, the number of years. Then there are min nodes for a particular player, let us say player 1, and max nodes, let us say for player 2, because player 1 wants to minimize the problem, and therefore player 2 who wants to defeat player 1 will try to maximize the problem. So terminal nodes have no children, and tree has got these alternating levels of max and min nodes representing player 1 and player 2. So here whichever player plays, so we have said player, this is player, so this would be player 1 or player 2 depending on which node. All nodes represent the state configuration. Terminal nodes are labeled by the payoff values, won or lose, and at a min node, the final payoff value at the min node is the minimum among all its successors. The payoff value at a max node is the maximum among one of successors. So this player 1 tries to maximize, so this is player 2 and this is player 1. So player 1 tries to maximize and it represents a max node, else it represents a min node. So here is a sample game tree. The rectangular boxes are the max nodes determining player 1, and the oval boxes are min nodes depicting player 2. And being large games, either the games terminate with some values as given here, these are terminal nodes, or in many large games like chess, you open up the game, you cannot open up the game till the end, so you open up the game till a certain level and you make some heuristics estimates of the position from player 1's point of view. And since there are 2 players, we will assume that it's like a zero-sum game in which the maximum of player 1 is, if the player 1 wants to maximize, player 2 will want to minimize. So this is a game tree which has got alternating max and min nodes, having some terminal leaf nodes. And in a game like chess, people open it up to say 24, 25, 26 levels, evaluate positions, put up these evaluated values or heuristics or estimated values, and then decide on one move that this person will take. So which is the move this person will take? If this is a min node, then obviously this person will take this move. This being a min node, this person will take 6 instead of 8. It will take 1, this will take 4, this will take 1, this will take 3, this will take 7, and this will take 8. So here the value at each of these nodes will be the min of its successors. At a max node, the value would be the maximum of its successors. It will be this node. Here it will be this node. Here it will be this node, and here it will be this node. Similarly, at a min node here, it will choose the minimum value here. This will choose the minimum value here. And at a max node here, this will choose the maximum value here. So this is how the best move that the person can make here is this side. Because we know that if a person makes a move, instead of making the move on this side, if by chance they made a move here, then the payoff, if the opponent could play in such a way that the payoff could be less than 4. Therefore, this person will make a move here. And in terms of this player 1, these are OR nodes. And these are AND nodes. So these are all AND nodes. In AND nodes, the max value is computed, and in OR nodes, the min value is computed. And that is how what we get is called the min-max value of the game tree. And it is the min-max value that we want to find to determine the action that is to be taken at this point in time. The question is, how do we compute the min-max value? So we now, in order to compute the min-max value, we resort to search. So we will first look at depth first search. And let us see how we do depth first search. So we come to this node, we visit this node. We then generate these two children, 2 and 3. And we expand this node. So this node is closed. Now when we have got 2 and 3 in open, then this node is opened and these two nodes are generated. As we move on to the depth first search, then this node 4 is created and this node and this node are generated. Now once we generate, so this is the first node to be taken out, this is the second node, this is the third node, this is the fourth node. Then we look at this node. And once we look at this node, what we do is we now tentatively back up 2. And we look at this value of 2 and we decide whether we want to go down and check the next one. We have no option but to check the next one, because that next one could have been 1, could have been 0, could have been 6, could have been anything else. So we then examine this node, and after examining this node, we know that since this is a min node, this value remains 2. After we see that this value remains 2, after having looked at this backup and this value remains 2, we back up this node and tentatively make it 2. Now, after looking at this node, we then expand this node. And this is the 5th non-terminal node to be looked at. This 5th node, which is this node, is now looked at. From here we examine this node, and after we examine this node, the tentative value backed up here is 6. Which means that at a min node we have value 6. And at a max node we have value 2. So there is no reason why we should not look at the next successor of this node. So we will look at this successor, and the value of this node being a min node still remains 6, and the value backed up here out of 2 and 6, so this value now becomes 6. Once this value becomes 6, this value tentatively becomes 6. Then this node is expanded. Once this node is expanded, this is the 6th node that is expanded, then its children 8 and 9 are generated. Then 8 is the next node expanded, which is the 7th node expanded. And from 8 this child is seen, and this child seen, this node's value becomes 1. Once this node's value becomes 1, then this successor is seen. The successor of value 10 is seen. This value remains 1, and the backed up value at this point from here becomes 1. Now at a min node we have 6, at a max child we have 1. So we now look at the next child here. This node is expanded. Once this node is expanded, this child is generated, and this value becomes 4. Then again this child is generated. This child is generated. The value remains 4. And out of these two values, 1 and 4, which is, because it's a max node, this value becomes 4. Now this side is completed. So this value backs up as from here. This being a min node, this value becomes 4. Now this part of this tree having been seen by depth first search, this value, tentative value of 4, is backed up here. And the only node that is left in the open list is this node. So this node is seen now, and these two children, 10th and 11th children, are expanded. Then this node is seen, and this 12th and 13th children are expanded. Then this node is seen in depth first search, and this is seen, and this value, definitely this value becomes 1. Now we have an interesting question to ask. We know that from here 1 will be backed up from here, and anything that is backed up from here will be less than or equal to 1. And we know that at this top node here, their value, which is a max node, it will never be less than 4. Therefore, irrespective of whether this value is 0, 5 or 55, if it is 0, then something 0 will be backed up here, and this value will never reduce before less than 4. If 5 comes, if 1 will remain here. If 55 comes, 1 will remain here. So looking at this tentative value of 1 and comparing it with the tentative value of 4, this being a min node and this being a max parent of this node, we see no reason to look at this edge. So this is where we effect what is called pruning. Pruning comes when the tentative value at a min node is less than or equal to the tentative value at a max node. If the tentative value at a max node is greater than or equal to the tentative value at a min node, then there is no point looking at that looking at the child below that min node. So having effected this pruning, we now back up 1 here. Then we again come back and generate this node. We check this child. Again we back up 3. And we have the same argument comparing 4 with 3. We prune this node. And this tentative value which comes here, from here 3 will be backed up here, and this tentative value of 3 is backed up here. Now we have a max node, parent max node, and a child min node. The tentative value at a child min node is 3. The parent max node is 4. And obviously we know that this value 3 will either become less than 3 or remain 3. Therefore nothing beyond this can improve the value of 4 for this max node. Therefore we prune it exactly here, and we don't need to see anything else beyond this. So this pruning is the depth first branch and bound, which we have seen earlier, being effected for game trees. So by employing depth first search, we can do a depth first branch and bound, which is called the depth first pruning technique. Now depth first search, when we looked at this node, we generated this child and this child, and we ordered them this way. We could do depth first search in the reverse order. We could do this first, this second, and we could order this in the open list this way. Then we would move in this direction of the search. I leave it for you to see that if I do in this direction of the search, obviously we will not be able to have the same pruning, and like depth first branch and bound is directional, we will get different kinds of pruning depending on the direction we take in depth first search. So I leave this as an exercise to perform. If I do it in the right to left fashion, what sort of pruning I would get. Let us look at another example where we have shifted it a little. Here we have another set of leaf nodes, and what we do here is we first look at this node, then we 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 look at this node. We tentatively back up 1, then we look at this node, and being 1 and 7, this is 1, so we tentatively again back up 1 here, then come and look at this node. We look at this child, we tentatively back up 4, then we check this node, this remains 4, this backup, because it's a max node from 1 and 4, this becomes 4. So this backed up value becomes 4. And this backed up value comes here, this becomes 4. This becomes 4, and then we examine this node as the 6th node, this node as the 7th node. We look at this becomes 8. Then we look at its child, the other one, and this value becomes 6. This value becomes 6. And this value is backed up as 6 here. Now, unlike in the previous one where we had a max parent and a min successor, we have a max successor and a min parent. Now the value at this node is 4. The value at this node from this branch is 6. This value 6 can only improve, and this value 4 can only decrease. Therefore, we say that there is no need to check this, because even if it reduces from this side or increases from this side, it is not going to affect this value. I leave it as an exercise to see that if we continue the search in the other direction, like we saw these two prunings in the previous example, we will see the same pruning. And again, you can do a left to right, left to right, or right to left, DFBB, which will give you various kinds of pruning. So what are the pruning rules? The pruning rules is that if you have a parent A and a child here, and what we have seen from these two nodes, we have seen A and B. A has a tentative value of 10 and B has a tentative value of 14. A is a min node, B is a max node. The value at B can only increase, the value at A can only decrease, and therefore there is no point seeing the node C. So this is a shallow cutoff between direct parent and child. And as we have seen earlier, there could be a deep cutoff. Here, this is a max node and this is a min node. Here the tentative value is 10 from this side. Here it is 5. Therefore, it is easy for us to see that the value of at D will never be more than 5. The value at A will never be less than 10. Therefore, there is no point seeing this node. And as we have seen in the previous examples, like here we had a min parent and a max child. Here we had a max ancestor and a min child. It is applicable for this alternative in a different way. So we can have deep cutoffs, shallow cutoff. The rule is the same. The rule is that the value, the tentative value at a max node, if that value is greater than equal to the tentative value at the min node for a parent descendant or an ancestor child situation, then pruning can be done. This pruning is known as alpha beta pruning in game tree search. So alpha value is a value at a max node, is known as the alpha value. This is the tentative value at max node. And the tentative value at the max node is the lower bound, which means that this value can only increase. The tentative value at a min node is called beta value, and it is an upper bound in the sense the value can only reduce. Therefore, the pruning condition is when the tentative value at a max node is greater than equal to the tentative value at a min node in a parent child or an ancestor descendant situation, we can prune. We have seen several examples, and this is known as alpha beta pruning, which is basically a depth first branch and bound pruning criteria, where we have got both max and min. So this is the algorithm. The algorithm again defines both the alpha and beta at a particular node. In a max node, it is the alpha which is important. In a min node, it is the beta which is important. So at a max node, for each successor, we look at the alpha value that is coming up from top and compute whatever we get and do the maximum. In a min node, for all successors, we compute the beta value and compute the minimum. And we use the same pruning criteria in both the cases. This is how we call it at the root and solve the problem. In this particular case, we will start with minus infinity and plus infinity. Then we will pass minus infinity plus infinity. We will pass minus infinity, minus infinity plus infinity, minus infinity plus infinity. And then when we start backing up, then we know that this will become 1 here. Then when we look at this node, this remains 1 here. This tentatively is backed up to 1 here. And then as you go down, you will calculate the alpha and beta values everywhere and finally define these pruning conditions. And these details we have already worked out. If you follow the algorithm, you will get exactly the same pattern. Now coming to the other aspects. How do we incorporate heuristics? Which means that at every node we know that we have the tentative alpha and beta values. These alpha and beta values came up only from the children, but these we know that one of them is an upper bound and one of them is a lower bound. So at every node we require 2 heuristics, and if we don't have them, we will put minus infinity plus infinity. One is a lower bound and one is an upper bound. And once we have these heuristics in place, we can easily incorporate these heuristics into the alpha beta pruning algorithm. The next question is, how do we perform best first search? That means now we have at every node some alpha 1, beta 1, and we generate children. Alpha 2, beta 2, we generate children alpha 3, beta 3, and instead of going depth first, how do we go best first? Till now in best first search algorithms like A star, we have seen that we will choose the minimum of the F values. If it is a minimization problem, we'll choose the maximum of the F values if it's a maximization problem. But in such multiplayer games or AND/OR games, where we have got min-max values to compute, it is not straightforward to decide which one we will choose. Because this would be like this, at a max node, we would have to choose from the alpha values, and at a min node, we will have to choose from the beta values. So there is a unique different kind of algorithm called the marking algorithm on AND/OR graphs, which comes from the AO star algorithm, through which a best first search in game trees can be defined. For the time being, I will ask you to think about how to go about doing best first search in game trees, and if we get time, we will discuss this in more details in another class. The second is when you have multiplayer games, when you have team games. Suppose we go to that Chinese checkers problem. We had 6 players. And now we cannot define it as a max and min, and one winning, one losing, because everybody wants to win. So what we will have is, at every node, we will have a vector of 6 elements, x1, every terminal node. So every terminal node will define the value for every player. And every intermediate node will also have a vector of 6 depending on the number of 6 players. So now if this is player 5 and we have got so many children which are to be played by player 6 followed by player 1, then from the 6 vectors which we have, the 5th vector, this person will choose the maximum of the 5th vector, which means that everybody will choose the maximum of their own game, because we cannot combine the values into one value because it's no longer a 2-player game. So we will now have to use a vector, or we'll have to use a set of values for us to determine the situation of the game with respect to every player. Then we have team games. And in team games, we will see that while we have got maybe 4 players and 2 teams, each player will play in such a way that they are gaining for the team, which means that there will be a consolidated team value, whereas there will be individual player values, there will also be a team value. So a player will not only try to improve his or her own situation, but will also try to improve his own team person's situation and try to create more difficulty and reduce the chances of winning of either of the opponents. Finally, in probabilistic games, for example, the car game that we said, brake game, if I press the brake so much, then the outcome can be x1, x2. Either the car will stop or the brake will fail. And there will be a probability of 0.995 and 0.005 for each of them. And we have to now calculate, because we don't know which side we will go. Therefore, there is no more deterministic situation. We will have to compute the expected value of the outcome. and it is from the expected value of the outcome that we will be able to create the game tree structure. In real life, games occur in economics, very similar to the prisoner's dilemma problem. Every action that you take, every policy that you take, number of players will play in their own way. We have these reactive control systems which I just talked about are real life situations of probabilistic games. And again, we talked about a car and other things where probabilistic games come in. So game trees occur in multiple ways. We have seen a typical example of the details of two-player deterministic games. And we have seen the alpha-beta pruning algorithm. But we have opened up the avenue for a large number of other possible situations. And each of these possible situations has got a deep theory and several interesting algorithms for us to work on. I would request you to have a look at these algorithms, but at least clarify yourself that this game tree search alpha beta pruning is a depth first branch and bound algorithm. We need to look at heuristics and best first branch and bound, and then we need to look at various kinds of other algorithms for this. Thank you very much.